In the previous section, you may remember that we looked at the distance a ball falls from a great height, and we defined a function d equal to 16t squared to show the distance after t seconds, and the distance was measured in feet. At the very end, we considered how fast the ball was falling with an average rate of change, but we asked the question, how fast was it falling at exactly t equals 3 seconds? To further explore this, we are going to look at t values between 3 and 2, getting very, very close to 3. So notice you can think of it as T2 is approaching 3, which results in delta T, the change in T between T2 and T1, approaching 0. Notice we are also going to see that the change in D is going to approach 0 because it's reaching a point where that change is not going to be as great because our time is going to be less and less. And you're going to see here, this gets very close to our delta D over delta T, and you can see it's beginning to approach a value of 96 feet per second, which is an estimation of the instantaneous rate of change. What we can define this as is we can consider that the limit of delta D over delta T, which is our average rate of change, as that change in time gets closer and closer to 0, in this case was 96 feet per second. Well, how can we formalize that without having to create a chart each time we want to explore this? Well, let's consider a relationship between slope and change in y over change in x. We have a graph here of y equals x squared. And we're going to look at several points and get closer and closer and see what relationships we can draw from these comparisons. Here I have the points 3, 9, and 4, 16. We can draw a line between these 2 points, and this line is called a secant line. It touches the graph in 2 places. Notice from here, we can determine the slope of this line by simply doing y2 minus y1 over x2 minus x1. And if you do that, you're going to determine that the slope of the line is a positive slope from left to right, but it's not exact. If we get a little bit closer, perhaps we shrink from 4 down to 3.1. Notice then we can calculate the delta y over delta x for these points, and that delta x is moved all the way down to 0.1 from the 1 that it was previously. When you calculate the change in y, you get 0.61, and this results in the slope of the secant line being 6.1. So now we have a secant line that's even closer to being tangent at the point 3. We can continue to do this and get closer and closer, making this number closer and closer to 3. And what we're going to soon find is that the limit of the change in y over the change in x, which is the slope of the secant line, as delta x approaches 0, in this case is going to get very, very close to 6. As it reaches 6, what we find is that the slope of the tangent line is indeed 6, and the tangent line equation can be written as 6x minus 9. We can now define what we're going to call the slope at a point on a curve, and we're going to tell it that the slope of a curve f of x at some point AB is exactly the slope of the tangent line, and this is indeed the instantaneous rate of change. Now notice the secant line, we're dealing with that difference quotient that we've been looking at so much. But what we're doing here is we are taking that secant line formula, and then we are going to get that delta h very, very small, or I'm sorry, just h very, very small. So x and x plus h are getting closer and closer together, which is a limit. And that is what we call the slope of the tangent line. That tangent line, this is also referred to as the derivative of the function. So how do the secant and the tangent line compare? Notice here, the secant line, we have the 2 points that we're connecting. This is our change in y and our change in x right here. So to find the slope of that secant line, we do the change in y over the change in x. All we're doing to find the tangent line is we're moving this point down, and then we're moving it down again, and we're moving it down again. So what's happening is we're making h get closer and closer to 0. Let's consider some practical examples of this to hopefully help you picture it. Imagine a function f of t that represents the temperature in South Carolina on a typical day, where t is hours since midnight. So in other words, when t is 0, it's exactly midnight. How might you describe f prime of 8? So what does f prime of 8 mean? That means what is the slope of the tangent line when x is equal to 8, or in this case, t is equal to 8. And for t to be 8, that would be at a time 8 hours after midnight, which would be approximately 8 a.m. Well, let's start by drawing a graph to represent this scenario. We have t here, and the temperature is going to be some value when t is 0 or midnight. And after midnight, between, say, midnight and 6 a.m., the temperature is likely to drop. But then at 6 a.m., it's likely going to begin to increase again. And then mid-afternoon, it's going to begin to come back down and maybe be about the same value at t is 24, which is midnight the next night. Now notice if we come to 8, according to our best guess, there's going to be a positive slope. So what we can say is we could describe the first derivative at 8, or the slope of the tangent line at 8, as being positive. If we consider f prime of 21, again, we want to go to where x or t is 21. And if we were to draw a tangent line at that point, it would have a negative slope. So here, the first derivative is less than 0. And we've already done part C, showing an approximation of what that graph may look like. Let's consider a situation where we have an arrow being shot in the air, and we have a function describing its height. We want to find the height at 3 seconds. Remember, interpretation is key. And all that means is we want to know the height, which the function tells us when t is 3. So for that, we simply just plug in 3 to the function. And when we do that, we get a value of 96 feet. Now, the second part here asks us to find the instantaneous velocity. We could find the average velocity if we were given 2 times, but here they want to know the instantaneous velocity. And if you remember, that instantaneous velocity comes from taking the limit of that difference quotient. So we want h to approach 0 between 2 points, t of plus h and t in this case. And t is going to be 3 when we get to the end. But we don't know how close we're going to get to 3. So to simplify this, we have to find f of t plus h, which is going to be negative 16 times t plus h squared plus 80 times t plus h minus f of t, which is simply, in this case, negative 16t squared plus 80t. And this is all over h. And then at the end, we'll take the limit. We'll bring that limit piece back in. Now, I'm going to let you go back through at some point and perform the math. But when you simplify all this, you end up with negative 16h squared minus 32th plus 80 over h divided by h. Notice all the terms have an h, which allows us to cancel h from each term. And we find that our difference quotient is negative 16h minus 32t plus 80. So now to find the instantaneous velocity, we simply take the limit as that h value gets closer and closer to 0. And because we're now dealing with a polynomial, we can plug in 0, which leaves us with an instantaneous velocity of negative 32t plus 80. We call this the first derivative of the function. And we want to know the value or the instantaneous rate of change when t is 3. So we now plug that into the first derivative, which results in negative 16. To interpret that, what that means is the negative tells us direction, and it tells us the arrow is moving downward at 16 feet per second. So the velocity is negative 16 feet per second in this case. The final question that's included in this one is find the time it takes the arrow to reach its peak. Well, here, the slope at the peak of the tangent line is going to be 0. So the simplest way to do this is to consider where is the slope of the tangent line, and we have the formula for the slope of the tangent line. Where is it equal to 0? Simplifying, we get negative 32t equals 80. Dividing both sides by negative 32, we get t equals 2.5 seconds. And if we look at our graph, that seems reasonable and is indeed correct. Last but not least, I want to make sure you're able to interpret graphs. So if we consider the slope at each of these points here, we want to decide if the slope is 1, -1, 0, undefined, greater than 1, less than 1, or greater than -1 or less than -1. So looking at these, if we look at the point A, first of all, we do note that the slope is going to be positive there, that if we draw the slope of a tangent line. And remember, we can count rise over run. And in this case, the slope of the tangent line is definitely going to be greater than 1. B, if we look at that line, we can draw a tangent line, and I go up and over. The slope in this case is exactly 1. Looking at C, you're going to notice here the tangent line goes straight across, so the slope is 0. D, if I draw the tangent line, again, I can go, it's negative, and it moves, it is going to be slightly greater than -1, so closer to 0. If we look at E, E again is a place where it's sort of changing directions. So at E, the slope is 0. At F, if we draw our tangent line, it's not quite changing at a rate of 1, so it's going to be less than 1, but positive. And G is going to be changing very rapidly. It's going to change a number less than -1 is the slope. And last but not least, looking at another graph, we can simply determine if the slope is positive or negative. Here we're going to have a positive slope. Here we're going to have a 0 slope. Here negative, here negative, and here 0. We can't interpret these exactly because we do not have labeled points.